system of linear equations might have a unique solution. Of course, it might have no solutions. Equations might be inconsistent. But in general, it could have a number of solutions, okay? There could be free variables, in other words. Now, the statement we want to look at here and want to make some sense of is this. The general solution of a system of linear equations, and that would be the solution involving any free variables as well as other quantities. But the general solution then can be written in this form. X equals x sub p plus x sub h, where x sub h is the general solution of the homogeneous system, the solution of the system that could be expressed as the homogeneous system in matrix notation would be this, okay? If A is the matrix of coefficients, then this would be the set of solutions where everything to the right of the equal sign is 0. Solutions of the system where everything to the right of the equal sign is 0 in each equation. Okay? Now, the general system would be like AX equals B, where B is not necessarily 0. Okay? So, again, we could write the general solution as a sum of solution to the homogeneous equation, general solution to the homogeneous equation, and then XP would be any solution of the actual system, any numerical system not involving any of the free variables and so forth. And this is an extraordinarily profound idea, extremely important in solutions of, let's say, systems of differential equations. So we want to get this general idea in our head. It's also very important for solutions of just plain old systems of linear algebraic equations. So let's just take this system. Okay, now we're going to go ahead and solve it by reducing the augmented matrix. And the augmented matrix being this one, and that's obvious, reduces in just a couple of steps to this, and then to this. Okay, so we end up with a row of zeros, meaning that we do have a free variable. We do have we have free variables. Okay. So our solution, and I'm not going to go through the details of that. I mean, these equations translate to this. We're going to let x3 be our free variable. We're going to call that S. And then from this equation, we get x2 equals 3/5 S plus 7/5. And then plugging that in here, we get x1 equals 2 plus what? Plus x3, which is S, minus x, well, plus x2, sorry, okay, it's, there's an error here. Okay, so I'm going to have to stop and repair this error as well as another one that I've repaired. This solution says never mind, there's no error. Okay, sorry. Okay, solve this for x1. We're going to get 2 plus x3, so that's plus s, and then minus x2, which is minus all of this. Okay? Now, the error that I made when we did this in class was I saw the 2 and the plus 7/5, and I just added them, and I got 17/5. Very easy thing to do if you're being careless or skipping steps, as I probably shouldn't ever do again. But of course, this 7/5 is inside of this binomial, which is subtracted, so it should have been a negative 7/5, which instead of 17/5 should give me 3/5. Okay, so we've made that correction, and now I believe the solution is going to work out. Okay, so what we have is our x1, x2, x3, which is our solution x. So we could say, okay, x equals this. is going to just be this. Here's our x1, 3/5 plus 2/5 s. And of course, s minus 3/5 s is 2/5 s. That's obvious. And x2 is 3/5 s plus 7/5, 3/5, yeah. And x3 is just s. And I had 0 plus s, which is sort of unnecessary. We just put s there. Okay? Then I separate that in a manner similar to what I did when we were looking at basis of a null space. Separate it into the numerical solution and into the solution that depends on our free variable. The solution that depends on our free variable is the solution to the homogeneous equation. If you compare with what we did before with null space, it's essentially the same thing, because of course the null space is the space of solutions to the homogeneous equation, okay? The space of solutions to the equation AX equals 0, which is what our homogeneous equation is. Now, I didn't write out the homogeneous equation, but that was shown previously, okay? So, now we can say that this is a solution to our equation, and we can plug in 3/5 and 7/5 and verify each of these solutions. And of course, z is 0, 3/5, 7/5, and 0. Verify each solution. And we can also verify that 2/5, 3/5, 1 is a solution to each equation. Just plugging in 2/5, 3/5, and 1, you're going to get -3, et cetera, et cetera. I'm sorry, we're going to get 0, because these are the solutions to the homogeneous equation. So, so we say xh is a solution of ax equals 0. That's our homogeneous solution, our solution to the homogeneous equation. And xp is a solution of ax equals -3, 2, 1. And that would be a particular solution. It doesn't matter what particular solution we use, because any other particular solution will differ from this one by one of these. A solution to the homogeneous equation. That's worth stopping and thinking about. Okay? So, we say then that AX is A times XP plus XH. That H is starting to look a lot like an N even to me. Okay? And by linearity, that's A times XP plus A times XH. And XH is a solution to the homogeneous equation, so AXH is 0. So we just have a solution AXP, and in this case, that's our -3, 2, 1. And where did I get -3, 2, 1? I didn't modify that part of the solution, okay? That would be 3/5, 7/5, 0. Might be a little hard to read the board. Okay? So that kind of verifies and shows where all this holds together. Again, think of how this whole thing is very similar to what you do when you find a null space.